Hello everybody. I'm going to be talking about intermolecular forces, and this is covered in Chapter 9 of the OpenStax textbook. Intermolecular forces really require you to remember electronegativity, Lewis structures, a little bit about dipoles and polarity and covalent bonds, and it's very, very important moving forwards in organic chemistry and biochemistry courses that you might experience later. So inter means between two things. So intermolecular means between two different molecules. And there are three types of intermolecular forces you will encounter mainly. There's hydrogen bonding, there's dipole-dipole forces, and London dispersion forces. Now, intermolecular forces are very useful. They can be used to predict the solubility of different things, boiling points of compounds, and they can be used to predict whether two things will stick together. We call these adhesion or cohesion, and also viscosity. The hydrogen bonding is the most important property because it's the strongest intermolecular force. And hydrogen bonding is a cohesion. It's an interparticle attraction between two adjacent molecules. Here you can see two molecules holding hands. That's a good way to think about cohesion. And these two water molecules are held together by hydrogen bonding. The hydrogen bonds of water make life possible. Here's a picture of some leaves, and because of the waxy acids, carboxylic acids that are present in leaves, the water tends to beat up much like water tends to beat up on a waxed car. We'll talk more about this in the future. Now, there are several features required for hydrogen bonding, and this is where you need to very carefully look at your Lewis structures. So here are two different water molecules adjacent to one another on the page here. This water molecule on top has an OH bond, so there's an oxygen bonded to a hydrogen atom. The other oxygen atom in the water molecule has a lone pair, and this is the required features that you need for hydrogen bonding. Okay, and what we do is we draw a hydrogen bond as this dashed purple line. Okay. And it's really just a dipole bond. A partial positive and a partial negative are attracting to each other, but it's very strong, and so we call it a hydrogen bond, even though it's not a covalent bond. Hydrogen bonding is also apparent in adhesion, and this is an attraction between two different types of molecules. In this case, we're going to be talking about water and glass. So here you can see these cartoons holding hands once again, but the molecules are different. On the left, you see a very complicated ball and stick drawing of glass, which is a silica, SiO2, and on the right, you see a whole bunch of water molecules. If you look carefully, you can see some dotted lines between the red oxygen atoms and the white hydrogen atoms of different water molecules and the surface of glass. Now, we know that water adheres to glass because of a meniscus that we observe very commonly in graduated cylinders, for example. And so that's because water is adhering to the glass surface through hydrogen bonding. Let me take you through the Lewis structures. So here's a fragment of glass on the left. You can see silicon and oxygen and a hydrogen, okay? And on the right, we have a Lewis structure for a water molecule. Now, glass actually has OH groups on the surface of the glass, and these are called silanol groups. And there's an OH group or an OH bond in the silanol or the glass surface that I've highlighted in yellow. Once again, we have a water molecule that has a lone pair on oxygen, and these two interact through hydrogen bonding. I like to think of that hydrogen between the two different oxygen atoms as the monkey in the middle, you know, if you've played that on a playground as a child, okay? So why do we have hydrogen bonding between these elements? Well, oxygen, nitrogen, and fluorine are three of the most highly electronegative elements in the periodic table. Remember, electronegativity increases to the upper right of the periodic table, and that's where you can find oxygen, nitrogen, and fluorine. And because those atoms are extremely electronegative, the oxygen-hydrogen, nitrogen-hydrogen, and fluorine-hydrogen bonds are very polar, okay? And remember that a polar covalent bond creates a dipole, okay? That's a polar covalent bond. And those partial positive and partial negative characters of the polar covalent bond create electrostatic interactions between other atoms, and we call those hydrogen bonds, okay? They're just a type of electrostatic attraction, okay? And so if you look at this figure on the bottom, you can see a water molecule on the left, and we have a delta minus above that oxygen. That means that there's a partial negative charge on that oxygen. And if you look at the water molecule on the right, you can see how the hydrogens are labeled delta plus. And that means there's a partial positive charge on that hydrogen. And once again, we just need to simply remember that opposites attract. Positive and negative charges are attracted to one another in chemistry. And so because of the extreme polarity of the OH bond, the delta plus and delta minus are a little bit larger than what you would normally expect in covalent compounds. It's so much so that we have a special type of bond. We call that the hydrogen bond, okay? So it's not a solid line, it's just a temporary bond between those two different water molecules, okay? Now, there are two requirements for hydrogen bonding, okay? The first requirement is that you draw your Lewis structure and you must physically have an OH bond, an NH bond, or an FH bond. That's criteria number one. And the second thing is that your Lewis structure must have a lone pair present on an oxygen atom, a nitrogen atom, or a fluorine atom. And those are the two requirements. Let me take you through some practice problems now.
Okay, so let's draw some Lewis structures for methane. Methane is CH4, so we've got carbon with 4 valence electrons, hydrogen with 1 valence electron, and this molecule obviously has no oxygen atoms, so it's going to be no hydrogen bonding. Let's look at methanol. Methanol is CH3. So this is a CH3 unit. And then there's an OH. So there's O and then H. And so carbon has 4 valence electrons. Hydrogen has 1 valence electron. Oxygen has 6 valence electrons. So let's go ahead and make our bonds here. And this molecule has an oxygen with a lone pair, and it physically has an OH bond. So this guy here can undergo hydrogen bonding. Okay, let's look at dimethyl ether. We've got a CH3, an oxygen, and a CH3. Carbon has 4 valence electrons. Each of these hydrogens has 1 valence electron. Oxygen has 6 valence electrons. Let's make our bonds. And yeah, so carefully make your covalent bonds, which are 2 electrons. And this molecule has a lone pair on oxygen, but it does not have an oxygen-hydrogen bond, right? There's no H bond to that oxygen atom. So therefore, this has no hydrogen bonding. Let's look at H2O2. H2O2 is going to have this skeleton. Hydrogen has 1 valence electron. Oxygen has 6 This oxygen also has 6. Let's create our covalent bonds and let's analyze. So we've got oxygen with a lone pair, and we physically have an oxygen-hydrogen bond. So this molecule here can undergo hydrogen bonding. NH3 has a nitrogen in the middle, 3 hydrogens. Nitrogen has 5 valence electrons. Hydrogen has 1 valence electron. Let's create the covalent bonds here. And let's analyze this structure. So we have a nitrogen with a lone pair, and we have an NH bond. So this guy here can do hydrogen bonding. NH4Cl. So this is going to be a molecule that looks like this. This is the NH4 is ammonium ion. And so nitrogen has normally 5 valence electrons. Okay. And hydrogen has 1 valence electron. Now for the ammonium ion, it has a +1 formal charge. So we need to use an eraser or something and erase one of these electrons on nitrogen. And when we do that, there's a plus formal charge on that nitrogen. Now when we create the bonds here between the hydrogen and nitrogen, we get the Lewis structure for ammonium. Chloride is an easier guy to draw. Here we just have chlorine, normally with 6 valence electrons. Now if we add in 1 valence electron for the -1 formal charge, we can put a negative charge on this chlorine and circle that guy. Okay, so let's analyze this structure now. We have no nitrogen with a lone pair. We do have a hydrogen physically bonded to the nitrogen. So because of this lacking feature, this molecule here has no hydrogen bonding. To do this problem, you have to realize that inter means between, so we need to draw 2 molecules side by side or one above the other. Pick either of these 2 molecules and identify the OH bond. Okay? So then on the other molecule, select a lone pair. Okay? So one molecule has a lone pair, one has an OH bond. Then we use a dashed line to indicate the hydrogen bond between these 2 different molecules. H2CO would have a skeleton that looks like this. Carbon has 4 valence electrons. Hydrogen has 1. Oxygen has 6 valence electrons. Let's draw our covalent bonds. And this molecule has an O with a lone pair, but it does not have a hydrogen physically bonded to a hydrogen. So this has no hydrogen bonding. Our other molecule, CH9a, has C with the 3 hydrogens. That's the CH3 unit, an O and an H. And carbon has 4 valence electrons. Oxygen has 6. Each of these hydrogens has 1 valence electron. If we create our covalent bonds, we can see how this molecule has two features necessary to make it possible to have hydrogen bonding. And the basic idea is that hydrogen bonding is a strong cohesive force between molecules. It would require more heat to break those apart. That means basically that it has a higher boiling point.